Thank you, everybody, for joining in. So we have an hour trying to explain to you what we think is potentially standard of care as an alternative for what we see now in the drug, opioid, psychostimulant, alcohol crisis that we live in, especially under the pandemic of COVID-19. I'm calling this also a pandemic for the reward deficiency syndrome as well. So we're going to go through a number of studies that suggest that, number one, the genetics of addiction risk score, GARS, scientific validation and clinical applications is something that I think we'd be very interested in exploring. So today we're going to talk about understanding reward deficiency syndrome, the brain reward cascade. All roads lead to dopamine, pro-dopamine regulation, the happy brain, and animal models of addictive behaviors links to hyperdopaminergia or low dopamine. So let's talk about reward deficiency syndrome. Basically, I coined that term in 1995, and the term is a kind of a relative failure of the dopaminergic system, which plays a major part in brain reward mechanisms. The syndrome has been linked to dopamine dysfunction. So there's two kinds of dysfunctions. There's an acute excess, where you got more dopamine being released, and then you got chronic deficit, where the dopamine release is reduced in the brain reward circuitry. The reward deficiency behavior includes drug and non-drug addictive, compulsive, and impulsive behavior. So it's a remarkable list. That's an umbrella term, which we'll talk about the differences in the DSM-5 and what other people are calling a new way of looking at how the brain resolves and works through symptom and molecular interaction rather than being carved out artificially by the DSM-5. So over time, we have developed this table which indicates the various addictive, impulsive, compulsive, and personality disorders that can be derived from reward deficiency and low dopamine deficit due to chronic functions, or even at birth. We're talking about DNA at this point. So it's trait and state, trait genetic, state epigenetic, or environment. And we have, as you can see, all of the substances related. We have non-substance related, spectrum disorders, disruptive, impulsive, and obsessive compulsive and personality. And the interesting thing is that many of these, not all, have been associated with a long list of genetic variants that relate to reward genes across the brain circuitry. So we know that RDS is something that is emerging. There's now over 200 papers in the literature specific for RDS, and there's over 1,200 specific now for reward deficiency. So it's in a growing field. Now, what is the brain reward cascade? Well, the brain reward cascade is something that I developed in 1989 with another colleague of mine called Gerald Kozlowski, and we published this, and it looks like something like this. The symbolistic view is that we are interactive with the various neurotransmitter systems, serotonin, enkephalins, GABA, dopamine, and as you can see, what we're dealing with is a cascade of events leading from serotonin in the hypothalamus, affecting the serotonin receptors, affecting mu receptor where the enkephalins work, then GABA is inhibitory that comes from the rapamynuclei to the substantia nigra. And then what we have is an effect on the glutamatergic system that drives dopamine release. GABA fine-tunes it from the substantia nigra, and then you get just the right amount of dopamine being released in the reward system to make us feel good, okay? And much more complicated view is we have interaction with cannabinoids, acetylcholine, and there's a lot of other neurotransmitters, second messengers. So it gets to be a very complicated system, but in terms of system biological approach, not a reductionistic approach, we know that if you could tap in to these pathways along the reward system, we'll have a much better chance of negating and mitigating abnormal craving behavior in the individual. So how do we get there anyway? So there are common neurochemical mechanisms between drugs and non-drug addictive behaviors. And there's a journal that is highly recommended for you to look at. It's the Journal of Behavioral Addictions. And this is by Zoe Demetropoulos, who's my associate. And by the way, is now looking at validation of the reward deficiency syndrome index. And what we have to realize, there's now a number of papers that have showed the overlap between the genetics of drug addiction and the genetics of behavioral addictions. So there's a lot of overlap. The difference being that drugs are certainly more directive in causing damage to the mesolimbic system, but over time, repetitive behaviors, including, of course, food addiction, gambling, sex addiction, has also a negative effect on the mesolimbic system of the brain. Now, all addictive behaviors, drug and non-drug, cause an acute release of brain dopamine. And that's very important, because if you're releasing dopamine acutely, that's why people are self-medicating. They need to get a dopamine fix, and that's how they get it. Now, the release results over time in a chronic deficiency of dopamine, and that's the hyperdopaminergia. Now, you can imagine if somebody starts with a DNA that has an innate lowered release, for example, of dopamine, or receptology of dopamine, or synthesis of dopamine, when you use drugs or behaviors that cause the release of dopamine consistently, you're gonna end up getting a double whammo effect onto dopamine function. Okay, so what we say then is when you have reward deficiency syndrome, you have a chronic hypodopaminergia, which may initiate at birth from the DNA or epigenetically from the environment. That means the impact onto the brain from the drugs or behaviors. Now, in a happy brain, that's what everybody wants. We have the DNA, the genes, direct the production, transport, and reception of neurotransmitters, so that the gene function remains homeostatic, balanced. Now, that word, homeostatic, I want you to keep in your brain, because that is very key for where we're going with this concept today. Now, certain polymorphisms, gene variants, of the reward genes that comprise the brain reward cascade have been correlated with chronic dopamine deficiency and reward-seeking behaviors that are reward deficiency syndrome behaviors. So it's very important to have to keep in mind the concept of RDS as we go forward. Now, Margaret Madigan, my editor, has developed a very unique kind of schematic to explain the happy brain and the unhappy brain. And if you look at one side, the unhappy brain, as you can see, just in one instance, if the GABA system is too strong, you're going to get a reduction of dopamine release at the reward site of the brain. leaving an individual with a deficit in dopamine, which can increase craving behaviors. And we know this is the case from the work of Wilhelm and others to show that when you have a decrease in dopamine, there's an increase, for example, in cocaine craving. Just as an example, the happy brain is what we're trying to achieve, where everything is in sync. And if you notice, the GABA now is in the right amount, the serotonin is right, endorphins are right, and then you get a normal amount of dopamine, and that leads to happiness. That's the goal that we want to achieve in terms of bringing about a happy brain in people, so that even if they're born with a deficit of dopamine through DNA variations or alleles or polymorphisms or SNP problems, you try to go to getting the brain in a homeostatic balance. Not up, not down, but balance. That's the goal. And then you can end up with a happy brain, as you can see. Now, what do we know about releasing dopamine? What are the stimulants that release dopamine from a presynaptic resting point? Well, interesting, food, which Mark Gold and associates have shown clearly that there is food addiction, similar to substance abuse addiction, can release dopamine at 6% above rest. Music, by the way, and I love jazz, as a lot of you people know, can release dopamine at 9%. Cocaine releases it at much more, at 22%. Sex releases it, and God knows we don't have that data yet, okay? So much more probably than cocaine. Now, when I say all roads lead to dopamine, I have been accused of keep saying dopamine, 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 when everybody knows there is the brain reward cascade, and there's all these neurotransmitters, serotonin, endorphins, GABA, acetylcholine, all interacting. Why would I say dopamine? Because we don't know at this point what happens after dopamine. And therefore, these roads that are interactive from the hypothalamus to the mesolimbic system and in between leads to dopamine release. So the end of the situation is dopamine released at the mesolimbic system to have effects on motivation, on cognition, on pleasure states. And the idea is that we want dopamine. We may not like it, but we want it. That's what we have to be very considerate about. So all roads lead to dopamine, according to Blum. Now, dopamine is released into the synapse of the brain to enhance well-being, motivation, and reduce stress. And reduce stress is very, very important. Now, stress induces the release of stress molecules like norepinephrine. And dopamine, by the way, under stress, gets released at 100% above rest to block dopamine's effect. So you have to have a pretty good dopaminergic function in order to reduce stress to overcome norepinephrine. Now, the release of dopamine causes feelings of well-being, motivation, and pleasure, like I said, and that is very important. So we need dopamine to function in order for us to go through our daily lives. So since 1970s, my lab has developed something we call pro-dopamine regulation. And it's the development of KB220 from 1968 to 2019. Along the way, I met my associate, Bill Downs, and together we came up with another variant called KB220Z, which is something that we have used currently and many, many times in the past. So I just want you to know that we are now using KB220Z. Okay? Now, you saw that. I'm sorry. We saw the happy brain, and now I want to talk to you about animal models of addictive behaviors links to hyperdopaminergia, low dopamine. Okay? So in 1978, I found myself at Colorado University taking a fellowship in animal genetics with Jerry McLaren. He was the father of animal genetics. And one of the things that we learned from that fellowship is that there are, for example, 3 different genetic strains of this was, let's say, mice. Now we know we got preferring rats, we have all kinds of other stuff. Then in the beginning, we were looking at mice, and we had 3 different strains. We have one strain that was DBA, and the DBA mice, they do not like alcohol. CHRs didn't know whether they like it or they don't like it, so they were kind of the bistro wine at dinner type. And then we had the mouse C57 blacks that ended up black. I don't mean to be that. We had a Black Lives Matter. We got to be careful. C57 mice. We have to realize the animals that love alcohol. So we wanted to find out, why is that? Why is there such a difference? And one of the things that we found out, and don't look at this next slide yet, is that one of the main reasons there's a difference is that the C57 black mouse have low levels of methionine and kephalin in the brain, the endorphins. And the C3s are in between, and the DBAs at the highest level. So we published in the Proceedings of National Academies of Sciences that one of the reasons why we have this genetic differential between these strains of mice has to do with the level of enkephalins that they have. Low enkephalins, increased drinking; high enkephalins, decreased drinking. The second thing is, what about stress? And it was found in studies from people at Ohio that if you stress an animal, for example, a rat, by making him force swim in cold water, the endorphins go down and the drinking goes up. So the stress-induced effect on the endorphins, which definitely causes a reduction in dopamine release, and craving behavior for alcohol goes up. The third thing is, let me go back a minute, because I'm not showing you, I should, is that we showed in an experiment that's published in Science in 1982 that if Syrian golden hamsters are drinking alcohol for 1 year and you measure the endorphins in the brain, specifically neurochemical, in the areas of the brain that have to do reward, the enkephalins and the synthesis are completely reduced, almost zero in some cases. So alcohol can also induce a toxic effect in reducing the synthesis of endorphins. And this has been shown to be true with opiates and benzodiazepines and even cocaine and alcohol. So that's very interesting. So we have these 3 effects that can affect our intake in terms of drinking alcohol or drugs. The formulation for the pro-dopamine regulation is as such, and I don't have the time to go over every little of this, but as you can see, we are using substances to, in a sense, bring about a systems biological approach, not a reductionist approach, to affect the entire brain reward cascade, which is opiate peptides, dopamine, serotonin, GABA, serotonin, chemical methyltransferase, enzyme, matter catalyst, glutaminergic, and so forth. Now, in many, many studies, and by the way, there are about 44 studies now on either KB220 or KB220Z, We could show that we can reduce craving behavior very, very nicely. We can show that we can affect relapse in terms of cocaine, alcohol, and heroin. We showed those over a number of studies with very, very significant differences, as you can see. We also show that one of the most important things in the clinic is AMA rate, which means against medical advice. And as you know, people come into treatment, even if they're forced, and they can run out of treatment without medical advice. And we actually can block that significantly by using this pro-dopamine regulation. And this pro-dopamine regulation was a basic formula. It had nothing to do with the genetics until 1990. So up to 1990, we were just using a basic formula that was KB220Z, or the earlier version, KB220. But as you can see, you get nice blockade with the AMA rate. And as you can see that very well. Now, more recently, I mean in 2000s, this is probably 2015, 14, I worked with Marcelo Fimo at the McKnight Institute, Brain Institute in Gainesville, in the University of Florida. And they had a beautiful setup to study resting state functional connectivity, which is $1 million magnet, but for rats, not for humans. And we actually studied whether the new adaptogen KB220Z induces functional connectivity of brain reward circuitry. Now, why is that important? Elliot Stein and Nieder suggested that alterations of the resting state functional connectivity, especially when it goes down, can be a prefront or an antecedent to craving behavior in the human. And therefore, we were looking to see in animal models whether or not KB220Z can actually induce a change in functional connectivity in the resting state. These were naive animals, so that we just wanted to see what happens in naive animals. And the answer to that is, and this is published in PLOS One in terms of looking at the KB220Z and functional connectivity in the reward circuitry. And as you can see, the placebo compared to the use of KB220Z, and this is 15 minutes after they received, the animals received the KB2O, and we're looking at the nucleus accumbens. You can see, excuse me, sorry, you can see that we have a very, very nice activation across that system. Now, we do know from subsequent work in the same paper that it's very specific to certain important parts and regions of the brain, and it's not all over the brain. So it's very regional specific as well. That's very, very important news. Now, in taking a look at human work, we actually showed that in abstinent heroin addicts, where we have placebo versus KB220Z 1 hour after taking it orally, as you can see, we brought about a interesting dopamine homeostasis. And the reason why we can say that is that if you look in the purple top part of the slice of the brain, what you see is that there's an increase now of dopamine, and where there was in the cerebellum high activity of dopamine, we now balanced it. So that gives us a view that not only are we getting balance, but we're also getting an increase in resting state functional connectivity from the use of KB220Z in the human. Okay, so that verifies and agrees with the work that we did with FIBO in the animals. We also show that in psychostimulant addicts, we can bring about a relaxation whereby we got increased alpha, increased beta activity, very significantly. The increased alpha and the increased low beta, which gives us the Herbert Kluger relaxation technique that is used in neurofeedback. So we have a very interesting kind of effect in absolute psychostimulant addicts from KB220Z as well. So we think that this all points to an interesting potential standard of care in the addiction field. Now, one of the things that seems to be a very important emerging issue is that when we treat opiate addicts with methadone, buprenorphine, Suboxone, the problem is that we're switching one opiate for another opioid. We know from work that I did that when you have long-term chronic Suboxone, the individuals look like they're zombies. Not everybody, but we have done that study. That study is published in PLOS ONE. You can look it up. So the idea is that naltrexone, which may have a heuristic value because it does not cause addiction, it blocks dopamine, and you bring about a psychological extinction. The question is, can you extend, even in the injectable form of naltrexone, which, by the way, compliance is not great, it's life, meaning can we increase the chance that by combining our pro-dopamine regulator with naltrexone, can we increase the likelihood that we can extend the utilization and the compliance to naltrexone? And we did an experiment in 2004, and I believe my dear friend David Smith is on the call, who did this work with me with our dear friend Tom Payne. And what we showed is that when 1,000 people that took the rapid detox methodology of using long-acting naltrexone, and in 37 days they relapsed opioids. When we coupled that with only a dozen of the naltrexone plus KB220, we extended the life to 262 days, which, by the way, was very significant. So this is a way in which we may be able to look in the future of combining dopamine regulation along with naltrexone, and then finally remove the naltrexone and keep people onto the pro-dopamine regulation as standard of care. That's the goal. So just in case, as a summary, I don't want to go into all of this, but this is a spoken well. In the middle, you got the neuronutrient KB220, and all around it, you got evidence for studies that have shown the positive nature of the neuronutrient KB220 in all of these studies. So, as I said, we got 44 of them, and double-blinded, triple-blinded, pilot studies, case studies, suggesting the importance and the important heuristic value of balancing the brain in a systems biological approach rather than a reductionist approach. Now, in part 2, we're going to talk about finding the addiction gene. We're going to talk about GARS, predictive severity, the drugs and alcohol reach studies, nature versus nurture, can the environment epigenetic be involved epigenetically, and what are the solutions that we talk about. And of course, the development of GARS, and that's what we're going to talk about now. So, finding the addiction gene. This first led to the identification of genetic basis of the genetic addiction risk score. Now, in 1986, I found a pathway to move my dear friend Ernie Noble to obtain a grant from the Seaver Foundation for $500,000 to start a search for an actual gene associated with alcoholism. At that time, all we knew is that there was work by Lawrence Goodwin, Schuckert, a lot of other people, Leonora from NIH, that, hey, there must be a gene or a set of genes that associate with familial alcoholism. Nobody knew what it was. Now, excuse me, I don't have the time to go over all of it, but the long and short of it is, in 1990, we published our results in JAMA. And what you see here is a graphic representation. We found that the dopamine D2 gene had a variant called the DRD2A1 allele, which, by the way, showed that there was an extra added SNP at 6.6 compared to the A2, and that we found that 79% about of the people that we know are alcoholic, based on them having a post alcoholic survey, because we used people that were deceased, and we used the brain tissue, we showed a clear association between carrying the DRD2A1 allele and the DRA2 A2 allele. And what we found out subsequently when we did binding studies, that those carriers that have the A1 allele compared to the A2 allele, nothing to do with alcoholism, we found that the individuals that had the A1 allele had almost a 40% reduction of the D2 receptors in the brain, which is something that we don't really want. And when we look at this, it turns out that 1/3 of the United States carries the DRD2A1 allele. And that shows that, you take the whole western part of the United States, that's over 100 million people, okay? And we're saying that over 100 million people can carry the A1 variant. And there was controversy in the past, and today it's very highly accepted that the DRD2A1 allele is a major culprit in addiction. But it varies according to ethnic groups. 50% African Americans carry it, 58% Hispanics carry it, 72% Asians carry it, and of course, Native Americans have it 85%. So it's a very interesting first gene to associate with alcoholism. But it isn't alcoholism per se that we have. We have a reward gene. This gene is associated with reward. And what we want to show you here is that what we're looking at is a change of a SNP. So genes govern the function of neurotransmitters, synthesis, degradation, receptor transport. Risk alleles or variants that cause chronic low dopamine that can give a hyperdopaminergic was chosen for the GARS based on functional studies. So we were interested in those alleles in the brain across the reward system that brings about low dopamine. And these alleles show an association with reward deficiency syndrome behaviors in hundreds to even thousands of studies. Now, the development of the genetic addiction risk score. Now, what happened from 1990 until about 2014 or so, my lab, and of course laboratories all across the world, were increasing the studies of many genes, risk alleles across the brain reward system, okay? And we developed something called GARS, genetic addiction risk score. Now, what we did is we decided to take a look at a number of these risk alleles or variants across the brain reward system. And we looked at the dopamine 1, the 2, the 3, the 4, the dopamine transporter gene, the serotonin transporter gene, the mu receptor gene, the GABA B3 receptor gene, monoamine oxidase gene, and the catechol methyltransferase. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And by the way, 11 alleles. And we did our first study, but our study was in Colorado. But when we looked at the literature to see what is indeed the association of not only the 10 genes, but the risk alleles that we picked for the GARS test, we found 110,241 cases of substance use disorder compared with 120,520 non-set controls. Now, taking a look at this, there's a high effect size, and there's definitely a significant association in favor of each allele to load on to cases compared to controls. We don't think the controls are great, because in order to do controls, we really need to have reward deficiency syndrome-free controls. I don't have the time to talk to you about that. But anyway, the controls are good enough to show that we have a significant association. But by the way, 0.05 is only the minimum. We have not done the final meta-analysis yet to give us the exact effect size. So that's in the work right now. Now, the genetic addiction risk score, examines the combined sum of many related polymorphisms to determine genetic risk. Polymorphisms equal gene variants. Is the sum of the number of risk alleles or gene variants as measured by the panel of genes rather than any one gene alone. This genetic addiction risk score is based on functional polymorphisms of reward genes. And what we do is we don't do a polygenic score. All we do is count the number of genes that an individual carries. That's important. Now, GARS predictive severity of drugs and alcohol research study. Well, what we had to do is find out what is the clinical association for a prediction that when you carry a certain number of these gene variants, you have either high or low, or let's say a high increased risk or no high increased risk of addiction severity. And we used alcohol addiction severity as one way to show that. And by the way, we also use a non-specific drug cohort to also show drugs, but not specific to opioids, okay? And we did that, and we used a mandated, validated test that I'm sure most of you know called the Addiction Severity Index, ASI. And what we used is a cohort of over 400 people that we genotyped, and 273 of these individuals derived from the very diverse 7 chemical dependency clinics in the United States, took the ASI, had the GARS score, and then to the University of Colorado, we did the genotyping with a Brett Habersteck and Andrew Smolin, developed a very clear understanding showing the clear association of whether or not you have 7 or more of these risk alleles, you have a high increased risk for alcoholism. Below 7, you do not have a high increased risk for alcoholism. With the non-specific drugs, because it's illegal, we're not sure all the answers, it only took 4 of these alleles to show an increased high risk for drugs, not specific, and a low for a low and no increased risk for drugs, not specifically. So the studies are shown here, and as I said, they definitely indicate a strong study indicating that we actually have shown that the GARS can predict the addiction severity to alcohol or for drugs based on the ASI as a clinical assessment tool as a validation. And that ASI has been validated in many, many, many studies across the globe. So significantly, we show, using chi-square analysis, that in terms of drugs, we have an overall risk of 0.05, so that's important with the ASI. And we showed that with alcohol, it's at 0.004, And age was actually also shown as a variant, which we also showed to be significant at 0.01. So what we're showing here is that it's a summary indicating that the ASI, as utilized, that normally predicts addiction severity, which is used in clinics, can also be used to help us associate the GARS test as a predictor of severe alcoholism or severe drug addiction. Thank you. Now, the opioid crisis. Well, as you can see, we have a major problem. We know now there's 185 people dying every day. It's increasing with COVID-19. And what we were looking for, and we did this work with Mark Moran, and the concept is, can we use the GARS test to predict when somebody comes to a pain clinic whether they may have a high risk for opioid addiction or drug addiction or alcoholism? And we did a study that actually now has 120 people, and the risk for GARS is way over 90%. Alcoholism is over 70%. So that means that people are generally coming in to treatment programs that have accidents. Young people, older people that come in and they are asking for opiates for pain. We have now a way to remove guessing. We have a way now to say, well, wait a minute, let's use in the beginning, a non-opioid type drug or a less problematical drug, like tramadol maybe, and let's see if we could put you in a bucket that says we've got to monitor you more carefully, so that we now have a way to do so with pain clinics, which we think is a very important standard of care, so that we do not guess. We know what we're up against. And by the way, it's been shown that in a over a year study that non-steroid analgesics actually feel better than chronic opioids. And I'm sure that Mark Moran is listening, he would agree. Now, the whole concept is nature versus nurture. So how do genes in a trait versus a state impact the whole reward system? Now, we know that there's a word now, epigenetic. And epigenetic is a way in which we know now that the environment can impact the expression of the RNA, which can affect gene expression. And it's a new field, it's maybe 12, 15 years old. So we know from a study that we did in a concept that was done many, many years ago, an equation or a mathematical model, that RDS is equal to genes plus epigenetic. So the phenotype, which could be RDS, or drug rate, is always equal to genetics plus the environment. Even the color of your eyes, there's always the genetic plus the environment. So the genes, the DNA does not change. That never changes. But through epigenetics, we can get methylation onto histones that sit on top of chromosomes that can affect the expression of any gene to RNA transcription or acetylation, which can enhance the expression. So we know epigenetics can affect the environment. That's very important. So we came up in 1978 with the types of craving behavior. We had type 1. You're born with the P, which is craving behavior, is equal to a genetic deficiency of neurotransmitters plus the environment. Number 2, stress. Craving behavior is equal to a normal neurotransmission, but the environment through stress decreases the neurotransmitters in the brain. And then finally, drug and substance use toxicity, where the genes are normal, but the environment or epigenetics causes a deficiency of neurotransmitters in the brain. Now, Let's take a look at nurture versus the idea of environment. Well, the answer is that yes, the idea of a trait staying there, that's DNA. But the epigenetics, the environment, everything from parental control to mentoring to teaching in all kinds of ways, to cognitive behavior therapy, to brain spotting, to a lot of ways, to trauma reduction therapy, all can affect the positive nature of how the brain works and can bring about epigenetic repair by affecting the RNA and affecting transcription of certain genes. So the question, can the environment be used to create balance, genetic and epigenetic brain function? Well, the answer is, of course it could. The final development of RDS syndrome solution system. So what we're saying is that we're taking the genetic addiction risk score, we're coupling it with the pro-dopamine regulator, and now we match the polymorphisms, the SNPs, the variations across the brain reward cascade that's affecting opioid peptides, serotonin, dopamine, glutamatergic system, acetylcholine, and we're changing the ingredients in the KB220Z to match the GARS results. This gives us a very interesting precision behavioral management or precision addiction management. And by the way, we are working on something called the Reward Deficiency Questionnaire, which now is in its final stages in Hungary with this psychiatric or psychological genetic study in Hungary, looking at the RDS questionnaire, coupling it with the GARS to get us even more information for validation. But what we're saying is that we believe that coupling the genetic addiction risk score with a semi-customization of matching the alleles and changing the nutraceutical that we call restorative, that we may have a very interesting way of providing precision nutrient therapy. So we use the GARS test to determine the polygenic alleles. We ascertain the new pathways involved by thinking about low dopamine or hyperdologic risk. We identify the new nutrient formulation of KB220 or KB220Z by an algorithm, but the algorithm is now an algorithm. We're not just counting the genes, we're actually doing an algorithm to come up with the right formula that is involved with a semi-customization that leads to one of 6 nutraceuticals that the ingredients have been changed according to the neurotransmitter systems, whether it's serotonin, we call it serogen, whether it's GABA, we call it GABAgen, whether it's dopamine, we call it androgen, whether it's metabolic, we call it catagen, and we have all these systems, we call it polygen, GABAgen, so we have all of these nice nutrients that are developed based on matching the neurotransmitter systems that show low dopamine. So we have a nice precision nutrient formulation. So where does this lead us? This leads us, for me, in this field for 60 years. I had a lot of controversy. I'm still here. And Mark, lucky thing I got through the program. I didn't die yet because you would have to take control of the PowerPoint because you probably know it as good as I know after 11 years. But anyway, more in terms of what I'm trying to say to the field is, look, we certainly get harm reduction by using the current MATs. Now, even including the use of a compensant, which is a dopaminergic blocker, because it's an MDA receptor blocker, which reduces dopamine. So What we're saying is right now, the pathway is to use an opioid, okay, to treat an opioid, to block dopamine if you're using, say, naltrexone or clamprol. And we're saying that why can't we consider the use of pro-dopamine regulation with the GARS, precision behavior management, as maybe a tool to bring about, okay, to bring about a stabilization and a dopamine homeostasis. So here is our analysis tree. Addiction and other reward deficiency syndrome behaviors. That's the problem. Parts of the problem: genetics, nature, epigenetics, nurture, RNA, GARS test, precision of new nutrient, preventive strategies, pro-dopamine lifestyle. Preventive strategy can be education. Results: attenuation of RDS behaviors, including substance and non-substance addictions, ADHD, PTSD, other RDS behaviors. All we're saying, let's do research, let's even utilize this in the meantime to help solve the opioid crisis and the drug crisis that we have, and we believe it's a pandemic, just like COVID-19. I want to leave you with this poem that I wrote, inspired by our dear friend Leonard Cohen. I've been trying to leave you every evening by closing the book. Every morning when I wake, there is more. I'm talking about my buddies, for all to look, and you are my buddies. Stay on track, nothing to ignore, because termination of our arduous work on addiction will only come when we find the answer and close the door. Thank you, Ken Blum.